Alright, so hopefully the audio works alright on this. It's a little sketchy earlier, but I think we'll be okay. Alright, so Thermodynamics 1, we're going to go through all 27 of the multiple choice. Here's the way this is going to work. So we're working on number 1. Boom. That way you can go through the video and you'll see this number and you'll know that I'm starting problem 1. So what I'm going to do is this. I'm going to give you sort of a hint on the approach, and then maybe what you should do is pause it. So if you're stuck and you just hear my hint out, or the suggested direction, and then try it. If you're really stuck, or you've already done it and you just want to know why you got it wrong, then continue to watch. So I'll kind of give a quick thumbnail of where I would go with it, and then I'll give a more elaborate description. I have not actually done these yet, so I have the answers in front of me, so I won't get any of them wrong in the end, but I may get a couple wrong on the way. We'll see. Gas undergoes an expansion in which 400 joules of energy is added to the gas by heating. The internal energy of the gas changes and the work done by the gas is. So this is based on internal energy, work done, and heat added. This should be fairly clearly a first law of thermodynamics. Change in internal energy is the heat added or removed, positive for added, negative for removed, and the work done on the gas. So positive if something does work on the gas, negative if the gas does work. And so it's going to be an application to that. So this is where I would pause it and see what you get. All right, now we'll finish it up real quick. So I'm looking at changes from 7 to 800. So it goes up 100 joules. It's added, so 400, positive 400 joules. And they want to know the work. So I got negative 300 joules should be the work done in that case. And then when they say by the gas, so this would mean, the negative here for us would mean done by the gas. So by saying that here, they don't require, then we won't necessarily have to have the negative sign. That's why that is the case. The fact that it's negative tells us it's by the gas. All right? And if it seems like I'm rushing, I kind of am, because I have probably 20 of these kind of things to do for AP1 and AP2. So, number 2, gas with a fixed number of molecules does 32 joules of work on its surroundings, and 16 joules of heat are transferred. What happens to the internal energy of the gas? So once again, this looks like first law of thermo. Just got to make sure we get the positives and negatives right here. So we want to know what happens to the internal energy, so that's this. We want to know what the change in it is. The gas does 32 joules of work. That is energy out of the gas. In order to do work, to expand its container, this is generally the way it happens. So it has a piston in the container, and when that container lid, that piston is pushed upward by the gas does work. And that is negative in this, because that means it's energy out of the gas. It has to give up, right? When you do work, when you lift heavy things, you give up your energy. You have to go eat more dinner, that kind of thing. So, so an expansion in volume, so the key idea here, and this is the other thing we're going to take from these, is what are the key ideas we have to know. If the volume gets larger, that means the gas did work and the work done is negative, because that's energy out of the system, is the way we're going to look at it. Now, so that would be negative 32 joules here. 16 joules of heat are transferred from the gas to the surroundings. That's negative 16. Right? Because the gas is transferred, the heat is transferred from the gas, out of the gas, negative. So the change in internal energy will be 48, negative 48 joules decreases by negative 40 by 48. All right. Number 3. Sample of an ideal gas in a tank of constant volume. All right. Just keep that in mind. Constant volume. It's an important point. The sample absorbs heat energy so that its temperature changes from this to this. If V is the average speed of the gas molecules before the absorption, and V2, I'm assuming that is, or V2, is their average speed after the absorption of the heat, what is the ratio of V2? So, this is not a first law of thermodynamics. It's, I believe all this is a, the average kinetic energy for a gas is 3/2 Boltzmann's constant times the temperature of the gas in Kelvin. So really we have two states. One of them, KE1, is going to be 3/2 Boltzmann's constant times the initial temperature, 300. KE2 is 3/2 Boltzmann's constant, 600 K. Now, what I want you, if I were you, I would maybe pause here and go, and just keep in mind that what is average, this is average kinetic energy. What is average kinetic energy? Well, it's the KE, average kinetic energy, is 1/2 the mass times the average velocity, usually the RMS velocity squared, but just think average velocity. All right, average speed, really. So this is what average kinetic energy, and each one, so there's a V1 and a V2, so my suggestion is let's put KE2 over KE1. Now, if you're wondering, but that's not the same as V2 over V1, but if you consider that it's 1/2 mV1 squared, sorry, V2 squared, over 1/2 mV1 squared, the 1/2s and m's go away. And really, you have V2 squared over V1 squared. So V2 squared over V1 squared is equal to, this is just a number, and so is this. Right? Boltzmann's constant is a constant, you can look it up. So this number would be on top, but you'd have to take the square root of it to get it down to get the V. So you're going to have 3/2 Boltzmann's constant. Actually, you don't even need to do that, do you? Because if you put this over top of it, you don't even need to calculate it. 3/2 Boltzmann's constant over 300. The 3/2 and Boltzmann's go away anyway. So really this ends up being V2 squared is equal to 600. That means V2 is the square root of 600 over V1, which is going to be the square root of 300. And so there's your ratio, the square root of 300 over the square root of 600. Not surprised that the square root shows up because kinetic energy is involved. There's that squared and velocity. When you start talking about velocity, it's almost certainly not going to be just a straight up ratio. So, by the way, that's going to be the square root of 2. Alright, so far I think I'm getting them all right. Number 4. Sample of a gas has a temperature of 200 K. If the speed of every gas molecule in the sample is doubled, what is the new temperature of the gas? Alright. Just like the last question, the key here is speed. If you double speed, what do you do to the if you double the average speed, which is what you'll do if you double everybody's speed. What do you do to the kinetic energy? Because it's 1/2 mv squared, if you double that velocity, you're going to have, so 2 times the velocity is going to give you 4 times the kinetic energy because of the squaring. So your kinetic energy is going to go up by a factor of 4. Well, that average kinetic energy is also equal to 3/2 Boltzmann's constant temperature. Well, you can't change 3/2 in Boltzmann's, so if this goes up by a factor of 4, temperature's got to go up by a factor of 4. So I'm thinking 800. Number 5. Sealed container with a lid of this area filled with an ideal gas. The container and the gas are allowed to reach thermal equilibrium with the surrounding air. 2,000 newtons. So I got area and force. Now, bell should be going off in your little head right now, right? All right, area and force. That sounds like pressure to me. Is needed to keep the lid from being pushed off the container. What is the absolute pressure inside the container? So, really, to me, first of all, pressure is force divided by area. They give us force and area. What's harder about, what makes this slightly harder, is they do want the absolute pressure. On that lid is pushing down the force by the 2,000, they'll call this the 2,000 Newton block, right? But there's also the force by air pressure. Now, normally it doesn't matter because the inside of the thing also starts at atmospheric pressure, and so they all start at the same thing. When your tire is flat, that's because it's not because the pressure inside the tire is 0. The pressure is atmospheric, the same as the outside. When you take the pressure of your tire, you're finding what's called the gauge pressure. So what we're about to find here is the gauge pressure. If we want absolute, the quick way to remember this, as soon as you see they want absolute, add atmospheric pressure to it. So our pressure due to the block is 2,000 newtons divided by an area of 0.004 square meters. I should be able to do that in my head, but you know what? I got a lot of these to do tonight. We don't need to tire my brain out. Divided by 0.004, boom. Alright, so I got, is that 500,000? Alright, so I got 500,000 pascals. Now, that's just the pressure by the block. We need to add atmospheric. So we looked that up. Sadly enough, Wellborn should know that. I want to say it's like 100,000? I think it's 100,000, but we're going to find out. It's on your sheet. Alright. So yeah, it's about 100,000. So plus another 100,000 pascals. So that should be, the absolute pressure is 600,000 pascals, or thereabouts. Which would be 6 times 10 to the 5th, if I'm not mistaken. 1, 2, 3, 4, 5. Yep. Alright. Six. A series of measurements are made of the pressure P and the volume V of a sample of nitrogen gas. I don't think the fact that it's nitrogen is going to make a bit of difference here. Kept at a constant temperature. Constant temperature. Make note of that. Internal energy is not going to change. I don't know if that's going to be important, but as soon as I see constant temperature, the internal energy is going to stay the same. It is desired to represent the data graphically so that the graph will be a straight line. Okay, so not too bad there. If the behavior of the gas is ideal. Okay, so let's start with, let's see, I would start with PV equals nRT. Now, the fact that it's constant temperature means this is a constant. R is a constant, and it's a sample of, so they're not adding gas or taking gas away. So all of this is a constant. P and V are varying. Now, we have two options. I don't know. It looks like most of these are. I'm not sure how you can have P over V as a function of V. Like, you can't have a variable on both sides like that. So these to me would be right away you get rid of. Looks like P is what we want to keep on the left. So if I keep this on the left, I'm going to divide both sides by V. P equals this constant. Remember, it's just a constant. Over here, when I divide by V, I could just put that over V, but I'm going to deliberately write this instead. And that's the difference between being really comfortable with this kind of problem and not. Because I know that this is just a constant. This is my slope. This is my y. This is my x. So when I plot this, I'll plot pressure as my y, and when I measure V, I'm just going to flip it upside down, and that's the number I'm going to plot here. If I do that, I will have a straight line, where this is the slope. So it should be P as a function of 1 over V. All right. 7. A small, well-insulated building. So we're on 7. A small, well-insulated building is kept cool on a hot day. A person in the building holds his hand close to but not touching a solid metal door. A solid metal. And this person is not touching the door. So their hand, represented by this thing here, is not touching the solid metal door. To the outside, and feels warmth coming from the metal door. All right, so he feels heat energy hitting his hand. Which statement best describes how the energy is transferred from the outside to the person's hand? So you have, we'll say, hot air, or sun's energy hitting it, but let's just say hot air out here. Those molecules slam into the door. Now, getting through the door. Some doors are actually hollow inside. So that's why I underlined solid. If they're hollow inside, then there's probably convection going on in there. But in this case, it's solid. So when energy is transferred through a solid material, that is conduction. So it's conducted through the door. Now, there is air over here, but convection is hot air rises, cold air sinks. So if it's convection, you would feel it up and down, like you would feel the hot air rising. This person is across, so it's not going to be convection. It's the only other way to transmit thermal energy, and that's through radiation. Infrared waves are coming off the door and hitting them in the hand. So this side of it is radiation, probably in the form of infrared. So thermal energy from the outside is convected through the door. If it's a solid door, no. Thermal energy from the outside is convected through the metal. No. In fact, there's only one that says thermal energy is conducted through the door. It's this one. And then the door radiates energy directed that is detected by the person's hand. This one is wrong because it says the thermal energy outside is radiated through the metal door. It's conducted. You could make an argument maybe that some of the infrared, but I don't think infrared would go through the door. No, it wouldn't transmit through. Some smaller wavelengths would, but I don't think infrared would. So this is your best answer right here. All right. 8. That one was? Okay. Alright, double question. 2 answers on this one. A student is given a sample of gas that's room temperature and is sealed in a container by a movable piston. Standard question. Which of the following adjustments would allow the student to increase the pressure of the gas? Select 2 answers. So we're going to increase the pressure. Well, there's really, to me, 2 ways. You could simply heat the gas while keeping the piston locked down, because if you don't, the gas could just take that heat energy and turn it into work and push the lid up and actually keep the same temperature. But if you seal the container and you heat it, then that's heat energy in. There's no way for it to get out other than just becoming a hotter substance, and even then it doesn't get out necessarily, but that's where it has to go. The other possibility is to push down on the lid. If you push down quickly on the lid, if you do it slowly, the extra heat energy, the extra temperature here will go away pretty quickly as heat to the surroundings. But if you push down quickly, you do work in. So if you delta U equals Q plus work in, if you push down on that lid and do work against the gas, and you do it quickly, there isn't time for heat to flow out of this thing. And this is what's called an adiabatic process. So you could do it so fast that there's no time for the heat to leave the container. The heat would be in the container, which would show up as a rise in temperature. The internal temperature would rise. So let's see if those answers are in there. All right, put the container in a tank at room temperature water. So in this case, instead of doing it quickly, they're saying, hey, we'll put it in room temperature water so that the temperature of the gas can't change. That if it tried to, the water would make it go back into equilibrium. So same kind of idea, but you definitely would push the piston inward. That would do it. That's energy in, so it should. So this works. Put the container in a tank of hot water and hold the piston in place. Yep, that keeps the volume the same, so no work, so the energy can go in this way, but can't get out through work. Boom, those 2. All right, number 9. An air-filled balloon is placed at the rest at the bottom of an open vacuum chamber. The chamber is then sealed and most of the air is removed. Which of the following will happen to the balloon? So a blown-up balloon is a balance between the pressure on the inside and the atmospheric pressure on the outside. The more air you put in, it expands, so the volume goes up, the pressure goes down, assuming everything stays at the same temperature, which you probably would for a balloon. So you have this situation, PV equals nRT, where this is going to be a constant. It's going to be at room temperature the whole time. So if you put more stuff in, that's going to increase the volume of it until the pressure, until it maintains that same pressure. So your internal energy goes up just because you're putting more things in it, interestingly enough, not increasing the temperature. If the balloon is sitting there and already has, and you reduce this, then this pressure inside is going to be more than the outside pressure. That's an imbalance in pressure. This thing is going to have to move until there is a balance. So I would think it's going to expand. Temperature increase? Now, volume increasing should not result in a temperature increase. It may be a temperature decrease, but not a temperature increase. Rise from the bottom. What they're trying to trick you with here, and I don't know if this is going to make sense or not, is in your head, something becomes less dense. But what becomes less dense is the air around the outside of this thing, not the air inside the balloon. And it will as it expands, I guess. But the air around you, what you're removing, this becomes less dense. And I think they're trying to trick you with buoyancy. I think you're trying to say, oh, the balloon becomes less dense and therefore would float. But it's not the thing the fluid itself is becoming less dense. That's a weird situation. So, no. I think it's just number one. All right. 10. Ideal gas in a closed container of variable volume experiences an increase in temperature while the pressure remains unchanged. What happens to the average kinetic energy of the molecules? Okay, so really what matters is this. Increase in temperature. I don't care what's going on. If the temperature increases, the average kinetic energy has to go up. So first of all, right, because temperature is the indicator of average kinetic energy. So the average kinetic energy, I'm assuming that it decreases. That's what this means here. It's bizarre, but average kinetic energy decreases. No. Average kinetic energy remains unchanged. No. I'm thinking this one's average kinetic energy increases. So it's down between these two. Now, in a closed container, I'm assuming that it has a variable volume. Okay. Increase in temperature, pressure remains unchanged. Well, if the pressure is unchanged, and this goes up, and this can't change, this has to go up. So I would go E in that case. Yeah, the volume's got to increase. All right, 11. An ideal gas is taken from initial state I for initial, at pressure P0 and V0 to a final state F, and that doubles the pressure and the volume. Figures below represent 4 possible processes by which the gas can be taken from initial state to the final. For which process is the work done by the gas the greatest? All right, PV diagram, this is what you need to know. PV diagram, the area under the line or curve or whatever is the work done. Either on or by the gas, but it's the work done. And not that it comes up in this problem, but if you have a closed loop, so some process that goes from, say, A to B to C to D and back to A, then the net work done by the gas is in there, or on the gas. All right, so we're looking for basically we're looking at these diagrams and trying to figure out which one of these has the largest area, just by kind of visually looking at it, really. There's that. This looks like it would have more area than A, so far B is the winner. But look at C. It's got lots of area. No, we don't count the vertical line part because there's no area under a vertical line. So I am going with, out of these 4 possibilities, this is the area of this one. That's definitely not a winner. I think C is my winner. I think this has the largest area out of something bigger than that. Yeah, bigger than that definitely, because we're talking, there. And then this is probably the closest one, but even it it's missing this part right here. Its area is, lower than the other one by that amount. So yeah, I would go with C in that case. All right, 12. Ideal gas may be taken from one state to another state with a different pressure, volume, and temperature along several different paths. Okay, quantities of always, okay. If you didn't get this one, It's because I didn't do a good enough job in making this next statement abundantly clear to you. If you go from one spot to another, so if you go from A to B, it doesn't matter how you get there, in the sense that it might change the work and the Q and all that, but the change in internal energy, remember the change in internal energy equals Q plus work. These two have very distinct internal energies. They're whatever their P times V is, or if you look at it, whatever their temperature is. But these two internal energies, those locations represent a set change in internal energy. In fact, look at it like this. The best analogy I can give you is from our AP Physics 1 days. If you travel from A to B, and all you care about is your displacement, does it matter how you get there? Your displacement, no matter how you get there, right? Your change in position, your displacement, is always that. So the change in internal energy is what we call path independent. It doesn't matter how you get from A to B. You could go like that. You could go like this. You could go like that. Doesn't matter. Those would mess around with what amounts of these happen. But the change in internal energy, if you have the same starting point, same ending point, it's always the same. So the only thing that I can say for sure that will not change is the internal energy. The others, it depends on, they depend on the path. How you get this number, there's all kinds of ways you could get, add or subtract Q and W to get that. All right, 13. Ideal gas with molecules of mass M. Okay, so we're going to do 13 and 14, and then I think I'm going to stop this video, and it's about 30 minutes long, and then we'll do the other half of this assignment in a second video. But 13 and 14, because they're basically the same question. One is one direction, one is the other. Here's the idea. When I went over with you at some point, I hope I did this with you. I'm assuming I might use this in other years. And we derived the equation that said KE, average kinetic energy, is 3/2 Boltzmann's constant times the temperature. We derived in class this equation. So if you want, and that's basically what this is. The same kind of principles are used here. We start with momentum. So it doesn't really matter, but they talk about vertical component. Okay, so a molecule of gas, a single molecule, will approach the top wall with a momentum of mv, with v is the average velocity. Obviously they don't all have that velocity, but it's the average. Hit the wall, and the kinetic theory of gases is they behave like tiny little billiard balls or super balls, and they have completely elastic collisions with the wall, and so it would come off with the same velocity but in the opposite direction, so it would have negative mv. So the root here is we do change in momentum, which is impulse, remember? An impulse is force times time. Notice they gave us a time. And then use that to come up with the force, and the area to come up with pressure. So that's kind of so we'll take that force, and from there we'll go to pressure, incorporating the area. So first of all, we got to figure this change in momentum. Be careful, don't tell me it's zero. Right? If something comes in positive and leaves negative, the change in this case, I'm going to go with let's do the final would be negative mv minus the initial, which would just be mv. So the change is negative 2 mv. Now I don't care about the negative. If I had chosen to make up negative the negative is just in this case is arbitrary. But the amount of momentum is changed by 2 mv. So we're going to go over here and we're going to say, all right, so my change in momentum is equal to 2 mv. Fine. That's my impulse. And the change in momentum is impulse, which means 2 mv is equal to force times time. That's another way to look at impulse. I look at it and go, I want to go pressure, so I need force. So I'm going to divide both sides by that time. So the force is equal to 2 mvs over time. Now, what's pressure? Pressure is force divided by area. So it's going to be this garbage divided by A. So it's going to be 2 mv. A and the T are going to be in the bottom. And that should be the pressure. Oh, quite careful. See, you got to be careful. It's not. This is the pressure caused by a single, right? This is just a single particle that we're talking about. All right. But the pressure on this entire side would be from not a single particle. So this is the most likely wrong answer. Because you can do all that work, you can be like me and be like, yes, I got it. But that's where the n comes in. I would have to take that and multiply by n for all the different particles that are going to hit that. They say n molecules hit the side in a cube at time t. So the n shows up. I'm going to take this number. This is for one molecule. I'm going to multiply it by n, the number of molecules. And that is the pressure on the side. So if you had this, you're doing really well. This is the right answer, though. For 14, you're going to work that exact same problem in reverse, or a very similar problem in reverse. You're going to start with the pressure and work your way back to the velocity. So let's kind of map it out. So we start with, we work in reverse. If we look at our previous one, I'm going to start with pressure is force divided by area. Actually, I'm going to start with force, I think. Let's try that. So let's see if we can work this out. So if I go, pressure is force divided by area. But force is really, well, actually, we just start with, I don't know if we could just know to start with this. That's the only problem. So I want to make sure I get, force is 2 mv over t. So I know this. This comes from the change in momentum and the time it takes to have it. Then I'm going to go, alright, so I need V, right? So basically I need to solve this for V. So let's see if I get this. P, oh by the way, N is in here too. So N here, N here. So P times delta T times area divided by 2 NN should be my velocity. And it's this guy right here, I think. So it's the same problem worked in reverse. All right, we'll pick up with 15 in the part 2 of this.